Astrophysics is pretty much the study of the smallest things in the universe. It covers all your fundamental forces except for gravity, so the electromagnetic, the weak, the strong. It tells us how particles get mass, and it allows us to classify them. To date, it includes 17 fundamental particles and 3 forces. And even though it's very, very good at making lots of predictions, we actually also know that it's incomplete. There's a whole bunch of big questions in physics that aren't answered by the standard model, and one of those is dark matter. Do you want to hit the slides for me there? Awesome. Cool. So what actually is dark matter? It was first hypothesized as a solution to explain what a whole bunch of really weird, anomalous astrophysical observations were being recorded throughout kind of the 70s and 80s. Even though we don't know exactly what it is, we can use these observations to work out what it has to do. So one of the things that accounts for 80% of the total matter in the universe, I think if everybody who was online was also in the theater, the ratio of empty seats to people would probably be about the same as matter to dark matter. It doesn't interact with the light or the electromagnetic force, depending on how technical you want to get. It's stable on long time scales, so it doesn't decay away like radioactive material. But it does interact with gravity, which is key to how we know that it's actually there. However, the big question is, if it doesn't interact with light, which is why it's very creatively called dark matter, then how do we actually know that it's there? I'll go through kind of the 3 main ways that we know that it's there by looking at how it can interact with mass. All right, so the first thing is galactic collision, so how mass interacts with itself. This is a very famous picture, and if you go on to keep studying physics, in particular particle physics, I promise you this is not the last time you'll see it. This is called the bullet cluster, and essentially what's happened is you've had one galaxy come through here and collide with another. So in pink, we have the distribution of mass of gas. So most of a galaxy is actually made up of hot hydrogen and helium gases. These are mapped in red here. And this is how we know there's been a collision, because you can see that something's shot through here like a bullet. In purple, however, we've mapped the center of the mass of the galaxies, which we can tell based on how the visible stars and things move. And the fact that the gas, which actually makes up most of the galaxies, doesn't overlap with where we know the mass is, tells us that there's a whole bunch of extra matter there that we can't see. The next thing is gravitational lensing, which is about how mass interacts with something called space-time. So if you've done any kind of special relativity, you'll know that our universe is made out of a space-time fabric that I like to say is a little bit like a trampoline. And when you put a heavy mass on a trampoline, it's going to bend it. And in the same way, if we have masses like stars and galaxies in space-time, they're going to bend it too. So you can see here, here's a plot of some of the heaviest objects in the universe that are bending space-time. The sun, a neutron star, a black hole, my eyes when I'm trying to write my thesis. And each of these guys are going to be bending our space-time trampoline more than others. And as they do this, when light comes in and it moves around it, it essentially is getting smeared. So you can see this in this picture here. So you can, I don't know if you guys can see from where you are, but there's basically a whole bunch of stars that are kind of being, and galaxies, sorry, that are being smeared out like this. And that's happening because there's this really big galaxy in the middle that's smearing them in this lensing way. And even though there's a big galaxy in the center here, we also see this happening when there's nothing in the middle. So it looks like there's no mass, but all the stars around it are behaving as if there is. So again, mass that we can't see. Finally, we come to the galactic velocity. So in the same way, I don't know if you guys have ever spun a yo-yo or a mass on a string, but basically the closer it is to your hand, the faster you have to spin it to keep it rotating. So exactly the same principle applies to stars within a galaxy. The further out they are from the galaxy, the slower they should move. So we expect them to follow this kind of curve. So as they get further out, they get slower. However, what we've actually observed is they stay pretty much the same speed no matter where they are, which means that there's not some kind of big clump of mass at the center of the galaxy. Instead, it's being evenly distributed, which is not what we see when we look at the stars. So basically, these 3 pieces of evidence tell us that there has to be extra mass that we can't see within the universe. And again, as I said before, if we can't see it, how can we work out what it is? So if it interacts with matter, we study it through its influence. We knew that it was there based on looking at how it influenced other things, and we're going to study it in exactly the same way. So this is kind of a standard, spin around. This is kind of a standard drawing of how we write interactions where we don't know what's happening. We're going to have a dark matter particle coming in, a normal matter particle coming in. We don't know what happens, so we just put a giant blob, and then we're going to say, okay, we've got normal matter and dark matter coming out. There's basically 3 ways that you can read this diagram. You can start from this side and say, okay, I'm going to start with 2 dark matter particles. They meet up, something happens, and they turn into 2 normal matter particles. I can read it up and down, where I say that, okay, I've got a dark matter particle coming in, it does something with the normal matter particle, and then they both go off their separate ways. Or I can read it this way and say, okay, I've got 2 normal particles coming in, and it outspits 2 dark matter particles. So these are 3 different ways to read the diagram, which means that there's 3 different ways that you can probe dark matter. I'll go through each of those quickly now. So the first one is annihilation, where you have 2 dark matter particles destroying each other and outspits something that we know how to detect. This is particularly powerful because obviously if it's regular matter, we have already designed a whole bunch of experiments on Earth that can see this. Because it's regular matter, we also know very well how much there should be if there was no dark matter, and we know how much energy they should have. So what we do is we put a whole bunch of telescopes like this guy out here called Fermi-Lat, which is pointing towards the sun. And we look very carefully at what's coming from the sun and see if we can spot any overabundances at certain energies. If we see some, then we know that this must be attributed to dark matter within our galaxy. So this experimental process is called indirect detection because you're not actually observing any dark matter. You're observing its annihilation. Sorry, I'll just move that so it's a bit easier for people to see. All right, next. We have collision, which is exactly the opposite process of annihilation. Instead of dark matter annihilating, it's our regular matter. So this is a picture of probably one of the most famous physics experiments in the world called the Large Hadron Collider. This guy basically collides these regular particles at massive speeds with huge amounts of energy to produce a whole bunch of other particles. So you can kind of imagine it, obviously a very simplistic diagram here, but we have our blue and orange particles colliding and then producing a whole bunch of other different colored ones, where you can kind of imagine that maybe these dark gray ones are dark matter. So there's a possibility that dark matter can be produced in these interactions. However, as I just said before, dark matter doesn't interact with any of our detectors because our detectors all use electromagnetic forces in order to observe things. However, we also know that energy is conserved. So if we go and add up the energy of all the particles that we do see being produced, and it doesn't equal the same amount of energy that the original particles had, it means that some of this energy has gone missing. And one of the places that it can go is into this dark matter. Next up, we have scattering, which is what the Sabre experiment that Bill and I both work on does. In this case, we're assuming that dark matter and normal matter can interact with each other by kind of bouncing off each other in the same way that you might have a regular collision. So in this case, you have dark matter coming in, hitting our target matter particle, and then this guy's going to have some energy transferred to it because of the dark matter. We can detect the energy of this target particle by using various ultra-sensitive detector components. So this is a picture of the Sabre experiment, and we'll explain this in a lot more detail later. What I'm going to talk about now is what detector scattering actually tells us. So when we go through the physics and all of our understanding of how dark matter could interact, what do we expect to happen inside these detectors? So this expression here basically just gives you the rate of a collision. This one is for dark matter. But you can apply the same kind of principles to work out the rate of collision of anything. Like if I'm walking out into the rain, you can use a similar thing here to work out how many raindrops are going to hit me. It depends on the number of targets that you have. Some particular properties of dark matter that I'll talk about in a second, called the cross-section and the mass. These are what we want to measure. The density of dark matter, so how many dark matter particles are hitting me, and then how quickly the dark matter is moving. These 2 things we can pull from astrophysical observations. This one we set up ourselves. So then all we have to do is put our detector underground, wait, observe some interaction rate, so some number of interactions that occur, and then we can calculate this value just here. So what do we expect this interaction rate to be? There's a whole bunch of different kinds of theories for what dark matter could be, but one of the most popular ones is called a WIMP, because physicists are excellent at naming things. It stands for weakly interacting massive particle because it's a particle that interacts weakly and it has mass. In this case, we expect that they have a particular value of mass and cross-section that is going to give it an interaction rate that is less than 1 count per day per kilogram of target. So think about that for a second. If you had like a kilo of flour and this guy could interact with dark matter, you'd only see 1 count per day. Now, I don't know how much you guys have studied about, general radiation or particles that come from the sun, but we have background signals that have a rate of over 1 million in the same mass and time period. So you're trying to pick out quite literally a needle in a haystack here, a single event over a day compared to 1 million. What we do have a bit of luck with, though, is the fact that dark matter has a really special feature. We expect it to have a modulating rate. Now, this happens because we've got kind of a cartoon version of the Earth in a sidecar as the sun moves through the galaxy and it hits kind of our WIMP flux here. Now, I hope you all know this could be groundbreaking science here, but the Earth rotates around the sun. So as the sun is moving through all these dark matter particles, half the time the Earth is traveling with it in this direction, and the other half of the time it loops back like that. So that means that the rate is going to change throughout the year by about 1 to 2%, and we expect to see more events in June than we do in December. So it's a bit of a gift that demonstrates this a little bit better. So you can see here we've got the sun and the Earth, and as the Earth is traveling kind of on the outer side of the sun, they're traveling parallel to each other. And when it's on the inside, they're traveling anti-parallel, which is when you get the minimum just here. So you can think about this as the same thing as when you're walking through, walking on the street on a rainy day. If it's really windy and the wind is blowing the rain into your face, as you're walking, it feels like you're getting a lot more wet because more rain is hitting you. However, if you're walking with your the wind to your back and the rain is coming back on you like this, you're almost outrunning some of the raindrops. So you're not getting as wet, and the interaction rate, in this case, is lower. All right, so I said I'd explain the cross-section and the mass. These are important because, as I said, the interaction rate is very, very low, but we can apply a couple of tricks to increase our chances of seeing an interaction. And we want to target what we think is most likely to be the cross-section and the mass number. So I'm going to talk through a bunch of detector concepts, and in the back of your mind, I want you to imagine that what I'm trying to see is the interaction from an invisible ping pong ball hitting something. All right, so the cross-section. Finally, after mentioning it like 3 times, I'm giving you a proper definition. The cross-section is a measurement of how likely an interaction is to occur. The actual name itself is a bit of a hangover from when we were actually trying to hit physical targets, like a bow and arrow kind of thing, where the physical cross-section and how big it is was a measurement of how easy it is to hit. However, when we think about physics, and in particular how dark matter might interact with normal matter, there's a whole bunch of other things that might come into play. So, I mean, there's not a lot of use, so I won't actually throw this out to, as a question, but there are some physics processes you've kind of probably come across that might influence how things interact. So things like if they have an electric charge, if there's any magnetism at play. Another thing that could influence it is how visible the target is. So if I'm standing at the back of the room and I'm trying to throw a ping pong ball against a whiteboard, if I know that my target is a big circle, but the circle is white and it's stuck onto the whiteboard, it's going to be hard to see. If there's a big black circle that I'm trying to hit with my ping pong ball, it's going to be a lot easier. You know, how many targets are there? If there's more targets, it's going to be easier for me to hit something. Are there any obstacles between me and my target? These are all things that influence the value of a cross-section for an interaction. So the cross-section in particular is going to depend on how exactly the target and the dark matter are interacting with each other. This is where it gets very mathsy and physicsy, so I'm just kind of try and leave it at that. But basically, to improve the chances of your interaction, you want to build a detector that's likely to have a very high cross-section. And by targeting the model that you think is causing the interaction to occur. So for example, I'm sure you guys have heard about protons and neutrons making up a nucleus. Some models of dark matter tell us that dark matter is more likely to interact with a neutron than it is with a proton. If that was the case, we would want to pick a target that has a lot more neutrons, like Zenon. Conversely, you might have a dark matter model that interacts more with protons than neutrons. So we pick a target that has more protons because that will have a higher cross-section. The second thing that we can kind of manipulate is the influence of the mass. So the relative mass of our target and our dark matter is going to have a really big influence on what we actually see. So imagine if I'm trying to hit a bowling ball and a beach ball with my invisible ping pong ball. They've both got the same size, so they've got the same physical cross-section. But if you can only see what the target is, if I throw a ping pong ball at a bowling ball, is the bowling ball going to move? No. If I peg it at a beach ball, is the beach ball going to move? Yeah. So if the only thing you can see is a target, an interaction with a beach ball is way easier to observe than an interaction with a bowling ball. So we try and pick targets that have a similar mass to what we think dark matter should be. So this is where I'm handing you over to Bill. I've talked about the interactions, so the physics and maths. It's going to generate a signal within a detector, which gives you a target recoil energy spectrum. And Bill is going to talk about the detection. So the physics and maths that turns this into a signal we can observe, which I have probably confusingly named an interaction rate, but it's more the interaction rate that we actually observe.
Actually, while they're swapping over, I'm just going to comment if you'd like to ask a question. Actually, put your hand up any time. Were there any questions for Maddy before she moves on? And Bill, if any questions come up from the chat, I'll just try to let you know.
Perfect. Okay. So yeah, I now get to talk to you about how we actually see these processes. So whilst I'm talking about this in how we look at for dark matter, it's exactly the same thing you'd use if you wanted to study other particles. So whether that's at a particle collider, or even in, if you're using it in like medical technology, like PET scanners that use particles to observe like areas of interest in the brain and things like that. So this idea is kind of quite universal whenever you want to observe a particle interacting. So there's two main measures to measure a particle recoil for dark matter. So one of the approaches is to use a scintillator, where we measure the energy of the recoil, and the other is where we use ionization that gives us a nice track we can measure for the recoiling particle. So I'm going to start off with what a scintillator is. A scintillator is just any material that when there's a particle recoil inside it, it gives off light. So it can be a solid or a liquid. This somewhat blurry photo here is a sodium iodide crystal. We keep talking about that because that's what Sabre uses, and we'll talk about that later. It can also be a liquid. So this, again, picture is a tank of a liquid scintillator with a PMT inside it. I even have a somewhat boring clump of it here. Unfortunately, the amount of light it produces when a particle interacts is really small, so we can't see it here. Yeah, so that's the scintillator. So how a scintillator actually produces light. So this is a crystal. So we're going to have a solid dark matter. Sorry for these low quality animations. This is my own handiwork and I'm not very good at drawing things.
Just not what you want me to change.
Yeah. So So if we start with some, in this case, we'll say a neutral particle. So it could be something we know, like a neutron, a gamma ray, or even a neutrino. It could also be dark matter for some theories. So this comes in and it will interact with one atom in our scintillator. So because this is a collision, it's like any other collision. It'll impart some energy and some momentum to our particle. So next slide. So this, in our case, might be enough for the particle to break the bonds in the lattice and start traveling through the scintillator. And when that happens, because this is now an ion, it's broken its bonds and it'll either be missing some electrons or carrying some extra ones. As it travels through, it's going to knock other electrons loose, creating an electron and an electron hole pair. This is kind of what you'll see sometimes in silicon as well. And the point is, as these go out, next slide, sorry. Our particle's now gone and we're left with these electrons and the spaces where electrons should be. And what happens is these are going to travel to something that's called the luminescent center. That's not how you pronounce it, but I'm just going to go through. And they recombine here. So now you've got the electron and the space where an electron should be. When they recombine, they give off energy and that gives off light. So suddenly we've turned a particle bumping another one into a light signal in our scintillator. And that's something that we can measure. So what would happen if we had a charged particle, right? You all know about alphas and betas, right? And then this here is a muon. It's just like an electron, but a bit heavier. So what happens if it's one of those? Well, we just get to skip a bunch of steps at the start, right? Because this is charged, when it travels through the scintillator, it's just going to knock those electrons off by itself. They'll then recombine and give us our light as normal. So what does this scintillation light look like? So the amount of light is proportional to the amount of energy deposited. But to give you an idea of just how much light we get for a dark matter-like event, again, the scintillator that we use produces about 30 to 50 photons per keV of recoil energy. So that's a very small amount of energy. That's helpfully done here, that 1 keV is 1.6 times 10 to the minus 16 joules, right? That's tiny. But for a particle, it's a reasonable amount of energy. So to detect this energy, we need something that's very, very sensitive to measure this light. And I'll talk about that in a little bit. So onto the other way we can detect a particle, which is ionization. So in this case, we have some gas in a volume, and we apply a strong electric field to our gas. So now our particle comes in, next slide. Again, it interacts with one of our gas atoms. We have a collision. So this atom now has energy and momentum, and it will be ionized sometimes. And as this travels now, again, it knocks electrons loose, and then it goes away. But because of our strong electric field now, our electrons are going to drift through the gas. And as they drift, eventually they reach the bottom where we can detect them. And not only do we detect them, we can detect their actual position and the time. And from that, we can reconstruct the path of our recoiling particle through the tank. So this technique actually lets us measure the direction of a particle. So as a very quick recap, when we've got scintillators, these are really good for looking at low energy processes like dark matter. We can even use them to detect energies that would only produce a single photon. So that's very, very low. Importantly, they can be very stable. Like obviously, this is a chunk of plastic. It's not going to change much over time. And you can potentially tell what kind of particle it is by how it interacts in the scintillator. If we compare it to ionization detectors, these are really good because they can give us directional information. They can tell us that a particle came in, well, the thing that recoiled off the particle came in this direction. The problem is it doesn't give us as much precision on the recoil energy, and you generally have less target mass, because remember Maddy was talking about it's the number of particles affects your rate. Obviously, a gas has a lot less atoms than a big solid chunk of something. Anyway, so I think we have a demo now, which is our cloud chamber. We might, do we have it? Is it working? Yeah,
Yeah, you can see them.
Yeah.
You can see the tracks there.
So we'll bring the camera up and have a look. So the cloud chamber is an ionization type detector.
People who are in my
You can probably come up to the front and have a look as well. So I'm not sure if you'll be able to see it, but what you can see here if you look is you can see these little like pulses. So these are the tracks of particles coming in and hitting it. You might have to like lean over the top to have a look.
You can see some things that look almost a little bit dusty. Those are actually tracks being caused by particles.
So they only last 2 or 3 seconds.
Yeah.
There you go, some good ones now.
So in a real experiment, we would use something to record where these tracks hit the ground.
Did you say this one gives alphas?
Yeah, we can swap the source. This is an alpha source. This is
Okay.
thorium coating on it. So we can put this here.
There you go. So if you remember, alpha particles are a lot larger. So you can see that they give off some bigger tracks in the tank.
I could watch these for like days. It's so cool. Yes, this is exactly that process that Bill was just talking about, the ionization, except in this case, you can see the tracks occurring.
Yeah. So I guess, are there any questions about this since we've got this all here?
I'm just watching, there's none coming up, so these guys are going to...
Do you have any questions? No?
No?
It's all right. Okay.
Carry on our merry way then?
I think we'll keep going. This will probably still be here and running afterwards if you'd like to come back, have another look and ask any questions about it as well. Thank you for that, Steve. Quite a bit of setup just to, for 30 seconds.
2 minutes. Yeah. I was just watching here, came through fine.
Perfect. Okay. So now to go back to how we detect a scintillator event. So detecting these, we just have a little sensor that reads out when an electron comes. But how we detect a scintillation event is going to be different, because how do you find a single photon? How do we turn a single photon into something that we can measure? And the answer is, it's with something called a PMT. So this is what I've basically been working on for the last 3 years. So I could quite easily bore you here. I'm trying not to. But if I stray too far, either please ask me a question or you can give me like some sort of hurry up sign. So this is a very complicated diagram, but it's all about how we detect a single photon. So the first thing is our photon comes into the PMT and it knocks an electron off at the photocathode. So this is the photoelectric effect. I know it's something you study quite a lot when we talk about the nature of light. PMTs wouldn't work if light at least wasn't a particle sometimes. So this will then knock an electron off, and this entire thing has a very high voltage applied to it. So this can be something like 1500 volts or even 2000 volts, and it increases as we go from this end to this end. So because we have a really strong potential, our electron is going to be drawn to this first metal stage. It's called a dynode. It's just a nice piece of metal that attracts the electrons. So as the electron comes, it's going to increase its energy, right? Because it's basically it's being drawn in. And when it gets here, it has quite a bit of energy. So when it collides, it suddenly knocks off a few more electrons. And then the same thing happens as it goes to the next one and the next one. And eventually, in a process that's basically like an avalanche, one electron will turn into millions of electrons. And suddenly that gives us a signal that we can measure. Okay, so next slide.
Did you want to show off the PMD?
Oh, yeah, I have a lot of examples of this since this is something I work with. So this is one of the ones that we'll use here. And it's just the same thing, but much, much bigger. So I'm not sure if you can really see. I can come in front if that's easier. So there's a faint gold glow on the front. This is because of the photocathode. And then if you look inside, you might just see a flat piece of metal. And that is the first of these many metallic stages. And then eventually we get a signal out from one of these pins at the back here. So I have quite a lot of these. And I'll talk about these ones specifically a little bit later because these are actually part of the Sabre experiment that we'll use. So what do one of these pulses look like if we have a single photon? So one electron's turned into millions of electrons. A million electrons still isn't a lot. So this is a pulse from a single photon. Actually, that one was recorded by exactly this PMT. I have to be careful not to drop this on camera because I will get in a lot of trouble if there's evidence of me dropping it because I was careless. But you can see.
Work out what the photocathode's made of.
We'd have a great teaching demonstration, but this is worth like what I get paid in 2 months, so I'm not rushing to drop that on the ground. So this is what our pulse looks like in green. You can see it's flat, we get a big spike and it's back. But to give you an idea of what this pulse is, the height of this pulse is only 24 millivolts. And the width of the pulse from here to here is only 16 nanoseconds. Right, so it's still a tiny pulse. It's just a lot bigger than one single electron. This one has a charge of a picocoulomb. So that's 1 × 10⁻12. So that's about 10 million electrons. So we've turned 1 electron into 10 million electrons, and it's still really hard to see. So whenever we measure these things, we need really fast and really sensitive detectors. And we do have those, but it's not easy by any stretch of the imagination. So I guess as a summary of how we detect a single particle interaction. So we start by using a scintillator to turn our recoil into a light, into photons. We then use a detector like a PMT to measure that scintillation light. And then finally, we can record these pulses like we had on the screen before and use that to then understand what happened. So from that, we can figure out the energy, how often it happened, and potentially based on the shape of that waveform, what type of particle caused the interaction. Okay. So I have another demo here. This is our muon detector. So as I said, a muon is just a heavier electron, and they're produced in the upper atmosphere from cosmic rays. So there are muons passing through us the whole time. And what this detector is it's exactly the same thing. We have a scintillator here that's coupled to a PMT. Now, unfortunately, because it's very sensitive to light, when we actually use these detectors, they always have to be wrapped in a lot of things to make them light proof. So that's why the entire thing is covered in black duct tape. But every time you hear one of those beeps, that's a muon passing through these scintillators, giving off light, which is then collected and turned into an electric signal.
So this is also the background I was talking about at the start. Remember how I said we had to observe 1 count in a day? These are all the counts that are becoming our background.
Yeah. So it's 1 count a day versus, it's just gone quiet for a second.
Turn on to the coincidence setting.
Oh, we can, and this was what would happen if you had, like this is all the noise that you really get. So that very rare pulsing was when we were already doing some work to try and get rid of some of the background. This is going to get very annoying if we keep listening to it, but this just gives you an idea of why it's very hard to look for dark matter, because we're looking for something very rare when there's a lot of other stuff going on to start with. Yeah. So I'll hand you back to Maddy for a couple of slides, if that's, I guess, are there any questions about that? No? Okay.
All right, so finally, we promised to tell you guys about the status of some of the actual searches that are going on. So the big one that we've been talking about quite a bit, apart from Sabre, is another one that uses sodium iodide crystal, which is why they're so important. And that's called Damalibra, which uses 250 kilograms of sodium iodide. There's a picture of the detector just here. So you basically have this cube that has all of those crystals inside copper enclosures that look just like that one over there. And then is placed inside a whole bunch of plastic and steel shielding. Now, what's cool about this detector is they've actually observed exactly the signal we expect from dark matter. So remember how I said we expected it to be changing throughout the year? This is their data. And you can see that it almost perfectly fits that exact same cosine curve that came up when I had my little GIF before. And they've been collecting data like this for 20 years. So I'm pretty sure that's longer than most of you who've been walking around the planet. So this seems like very, very strong evidence of dark matter within the galaxy. There is, however, and unfortunately, a but. Nobody else has been able to see it. So this is an exclusion plot and it's pretty common when you're in the field of dark matter. And I'll just kind of walk you through what it is. So remember I said before, the two things we care about are the mass and the cross section, so how likely it is to interact. So on the x-axis here, we have a mass, and on the y, we have the cross section. So basically what this plot is telling you is you can pick a point and say, okay, my dark matter mass is going to have a mass, my dark matter is going to have a mass of 100 GeV and a cross section of 10 to the negative 42 centimeters squared. So that's going to be about here, I think. Any experiment that has a line below that point is able to observe that particular dark matter model. So basically, you can construct these lines for each experiment, and then that experiment says, okay, if I didn't see anything, there's no way that dark matter exists in this space here. However, the signal that Dama has seen, which I just said was really good and looked like dark matter, lives in one of these two spots, which is canceled out by null results from pretty much every single experiment that's been conducted since then. So this is a really big problem in dark matter physics. We don't know how we can explain the Dama signal so that it's consistent with null results from all of these other experiments. I think Bill is now going to take you through exactly what these experiments are.
Okay. So the first thing is I'm eventually going to tell you about Sabre, which is the experiment we work on, but I thought I'd tell you what the current best experiment in the world is for not finding dark matter. So it's called Zenon 1 ton, and because physicists are very creative, you can guess what it uses for its target. It's Zenon. So this is a giant tank.
How much Zenon do they use though, Bill?
They use about 1 ton. Shocking, I know. We're great at naming things. If you like puns, this is the field for you. Physics, that helps too. So it's a giant tank, and it's located in an underground lab called the Gran Sasso National Laboratory. So in a very movie villain style, this is literally under the highest mountain in Italy. You enter it through a rolling door, and they've got giant caverns, and they use it for good, not evil, we're told. So this entire experiment is what it takes to be the best in the world at this. And in the very center, they have this picture drawn on that there's this tiny little tank, and that's the actual center of the experiment. Everything else is designed to find things that aren't dark matter, so they can make sure it's not in their signal. So again, it has nearly 4 tons of xenon, but as the name suggests, it only really uses just over 1 ton for its actual measurements. So not only is there this giant tank from all of these universities that runs it, they have a 3-story building that they use to run the experiment. So that has everything from computers and chemical labs to a break room and a control room. And this has been running for a few years. If we go to the next slide, you can see the very center of the experiment. And this is a scintillation detector. So this entire space in here is going to be filled by liquid xenon, which is a scintillator. And what you know, they've got PMTs at each end to read out the scintillation light. And this is the size of a person in height, and basically the person if they held their arms out. Yeah, so this is what it takes to be the best in the world. But then, if you're happy for me to do this. What about the Dama signal? So we are on Sabre, which is an experiment that is being built to test the Dama signal. Because if another experiment replicates the results, we can be pretty sure that it might be something like dark matter. So the whole point is we're using the exact same material, which is sodium iodide, to test it. And importantly, if the Dharma result is real, Sabre should be able to find it within 3 years of operating underground.
Not 3 years, in the next 3 years.
Oh, in the next 3 years.
Okay.
I'm not up to date with our current timeline. I apologize. So just as a very quick overview of what Sabre looks like, in the very center, we have our sodium iodide detectors, once again in their big copper tubes, and we'll go through that in a minute. This is then surrounded by another detector, which is filled with liquid scintillator, and that's red out, and we'll go through that again. And then finally, it's shielded with with steel all around it to block out radioactive particles, and we even have a muon detector on top, just like this one, except about 100 times the size. Anyway, so if we go to the next slide, where's Sabre going? Again, we're going deep underground. So Sabre's being built in an old gold mine in Stawell in regional Victoria. This is the photo of where the lab will be. We won't actually be working in this space. It's not very big. Our detector's 3 meters by 3 meters by 3 meters. They're building a lab here right now, so we don't have a photo of it, but that's going to be built very soon. So by being over 1 kilometer underground, we get nearly 3 kilometers of what we measure our shielding in terms of water. So by going 1 kilometer underground, we've effectively got 3 kilometers of water on top of our experiment. That helps block out the muons like we saw before. So instead of having them going that fast as we were hearing it, the rate's much lower, so we can actually observe dark matter. So onto the main part of the experiment, which for Sabre, which is our crystals. Sabre is using sodium iodide like Dharma, and we're using these big 5 kilogram single crystal bits of sodium iodide. So by single crystal here, I mean it's grown so that it's one continuous lattice of sodium and iodine atoms together. So these things take months to grow, and there's a lot of very, very sensitive handling. So they're great for a long-term measurement because they're solid, but one of the reasons we have to be so careful is because it dissolves in water. So this is why you can see, actually this is me and Maddy here handling it. Everything we do with these crystals has to happen in a clean room in a glove box. So we dress up basically like clowns to put on 3 pairs of gloves to finally be allowed to handle something. So in this case, this is the powder that ends up being used to produce these crystals. But this is how sensitive these experiments are, that we have to do all this work to keep it pure. Because again, Maddy was talking about 1 count per day per kilogram. When you're at that level, everything is too radioactive. People are too radioactive. There's enough potassium in bananas to just completely ruin our experiment if we left one in there with it. Yeah. So our crystal, sorry, actually I should have just, before we were there, our crystal actually will get placed in this. This is a mock-up of its little enclosure. And you can see here we have our dummy crystal and then the 2 PMTs that get paired with it on either side. This then goes in a copper tube, which then goes in our active veto. And the whole reason we have an active veto is that dark matter interacts very rarely, so it should only really interact once in our entire detector. So if we see something interact multiple times in multiple places, we can be pretty sure it's not dark matter. And that's why we have a giant tank of liquid scintillator that's covered with these PMTs, these big ones that can see single photons. And this is it doing exactly what it does. So we've talked about potassium a lot because that's the thing that most looks like dark matter. If you have a potassium decay inside the crystal, we might think it's dark matter, unless we could also see this gamma ray that's produced. And if it goes out, it interacts in our liquid scintillator. It produces scintillation light. We see it, and we know that it's not dark matter. We know that it was a different decay. Okay. So again, I told you I go on and on about PMTs. It's what I work on. I'm sorry, but I'm not really sorry. So we have our 2 different PMTs. We have the big one for the veto and the much, much smaller one. So these are made to see single photons. Because of that, they are quite expensive, and they're also handmade in Japan. So this one is like hand blown, nicely blown glass. And yeah, I quite like them. They are. They do look very nice. I guess if you're in person, you can come up and have a look. If you have questions about them, I'm happy to bring them up to the camera. You can also just not be as interested in them as I am. That's also okay. So I guess to summarize what we've done today, we've talked about how we know dark matter exists, what evidence we have for it, the different ways that it can interact with matter, and how we measure a particle interaction. I've gone on and on about that, haven't I? And then we have just how the hunt for dark matter is going. We have a result that looks pretty good, a bunch of results that say, no, it's not. And then finally, what the Sabre experiment is and what it's going to look like. So I just guess to conclude, if this really interests you, dark matter is one of the things that interests physicists at the moment. It's one of the most compelling areas to work on in particle physics. And if you actually keep studying physics, there's a good chance you could be one of the people that helps us find the results from this experiment. Right? Maddy said 3 years to get the first results. This will probably be going for 5 years, which is right about the time, if you're interested, you might be here doing a research project. So yeah, you could be the ones telling us the answer to this. Yeah. I think that's everything.
Yeah. Now there's 55 questions on the chat. So I'll take question 1 from Ben James. What was your question again, Ben? Ben hadn't asked a question, but I just thought if I'd asked Ben to ask a question,
you got me excited there.
No, I was getting all excited. Hey, actually, all right, Dorothy did say, all right, so the Dharma results wiggle up and down, you know, and they look like, do you expect yours to wiggle up and down the same way? I mean, isn't one in one hemisphere or the other?
I'll hand this over to the expert on what Sabre should look like.
Yeah, in the same way that Bill's spent the last 5 years now almost.
Let's not count how many years I've spent in a basement looking at PMTs.
Yeah, I've been doing the same thing 4 floors up, trying to work out what we're actually going to see in the PMTs. So Roger's right. One of the really cool things about Sabre, and in particular Supple, is that we're in the southern hemisphere. All of those other detectors we were talking about are in the northern hemisphere. So remember I said that we expect it to be modulating or changing throughout the year because the Earth is rotating around the sun. We can also have a lot of changes because of the seasons, right? So as one side of the Earth is further away from the sun than the other. One of the things that we expect to change with the seasons is the muon rate. So in the northern hemisphere, the number of muons that you expect to see has the same kind of look and feel as dark matter. So a lot of people have thought that this could be due to muons and not due to dark matter. However, in the southern hemisphere, they're opposite. Dark matter stays the same, but the muon shifts by 6 months. So if we see something in Sabre that looks like this, but just shifted, we know that it's not dark matter. If we see something that looks exactly like this, then we know that it probably is. Jacinta.
Why do muons shift northern hemisphere and southern hemisphere?
Oh, we need Mike.
I mean, we could get the person who spent 4 years looking at muons to do this, but are you happy to answer?
So, I mean, it has to do with the way that the Earth is tilted on its axis, right? So, I'll give you the microphone, actually.
We'll just pass it over. So it's because muons are produced in the upper atmosphere. So one of the things that affects them is the pressure up there. If you're doing chemistry at the same time as doing physics, you know the ideal gas law, right? So if you change the temperature, you'll change the pressure. That's true in the atmosphere as well. So in summer, which is what it is in the northern hemisphere in July, it's hotter, there's less air pressure, so the muons, the production rate will change. So the point is the muons change in summer because where they're produced has different conditions. They're produced in a different part of the atmosphere, so you get more of them. So one of the things is the muon rate doesn't just fluctuate with temperature. Whenever you have a thunderstorm come through, all of the experiments that look for muons see the rate change because you have a giant change in air pressure when a thunderstorm comes through. So that's why muons peak in summer when it's hotter in the atmosphere. I guess, does that answer I'm hoping that answers the question that was asked and I didn't answer something else.
You've clearly made everybody else experts. Now they don't have any more questions.
Job here is done.
How far underground?
1 kilometer.
Yeah, a kilometre. But because you have to drive in, it takes about 30 kilometers of driving to get there.
Oh, you just can't go straight down like Thunderbirds.
Oh, I wish. We haven't actually been yet. They had an official visit last week before.
But they took the important people like politicians and stuff like that. So soon.
I personally can't wait to go see it. Although in person, once we've got the air conditioning system, because apparently it's like almost 40 degrees down there.
Yeah. And because you remember when we were talking about the clean rooms that we had to wear the plastic clown suits? Because it's under a mine, you have to wear your proper high-vis like mining overalls. And then when you get there, you have to put your plastic clown suit over your mining overalls. So it's going to be unbearably hot down there. But please do physics. You don't just have to work in uncomfortable places. You can do cool things like visit the not evil underground lab in Italy, where they do cool things under a mountain. Yeah.
What happens when the radiation contaminates the crystals?
Good question.
That's an excellent question.
Maybe repeat it, yeah.
Okay, so the question was, what happens when the radiation contaminates the crystals? And I guess...
Yeah, I'm happy to take that one.
This is the banana question.
Yeah, the banana question. Do you maybe want to get the active veto one up again? Just because that's got a picture of the... Yeah, so one of the things that I didn't mention about dark matter is that we kind of know approximately how much energy it should have. So we expect it to be within around 1 to 6 keV. The problem with radiation is there are a lot of different radioactive processes that happen that have decay products at exactly that energy. So if you have them in the crystal like this, if we didn't have this liquid veto here, a radioactive decay would create, our scintillation event and detection in our PMT, and it would look almost the same as dark matter. So potassium in particular, which as Bill said, we talk about a lot and we worry about a lot, has a decay process that gives us a 3.2 electron, which is 3.2 keV electron, which is this guy here, and then our 1.46 MeV gamma ray. Now this is problematic both because, as I just said, it's right where we expect dark matter to be, but also, I don't know if you have the periodic table kind of set up in your head, but potassium is right underneath sodium. So chemically, the two are very, very similar, and it's quite easy for potassium to make its way into our ultra pure crystals. Now, Roger said that this is the banana question. And part of that is because a lot of the way we measure radioactivity is in terms of bananas. So Bill said we can't have any bananas in the lab because they're too radioactive. They're actually about 10 times too radioactive. So we have to grow these crystals so that they have 10 times less potassium than a banana does, because otherwise we would have our detector being overwhelmed by these kinds of radioactive events.
So I guess just as Maddy said at the very start, remember looking for a needle in the haystack. If we have other radiation there, that's just basically adding more hay to our stack as well.
That's the same size as the needles we're looking for.
Yeah. So searching for a needle in a needle stack might be a more appropriate example.
Yeah, because if it's a needle in a haystack, you just put a big magnet nearby and then turn on a leaf blower. I wish it was that easy.
What are the exact materials that are used in the detector to detect the
In here? Okay. So the exact material, it is really a smaller sheet of plastic, almost exactly like this, but just cut much thinner. So people are always very funny about saying what the exact material is here, because it's hard to believe. There's not a lot of buyers for it, but people do sell this. So typically, it's a very long chain plastic with a few very rare elements, mixed in. So for the most part, it's plastic. For our liquid scintillator, it's called linear alkyl benzene, which just means it's a really long chain of hydrocarbons with a benzene ring at one end. So it has the consistency of dish soap. So we have a 35,000 litre tank of dish soap arriving in about 3 weeks. Yeah, there's a scale to some of these things, but yeah, so inside here, it's just a bit of plastic exactly like this. I can't tell you exactly what it is chemically because they don't tell us what it is chemically.
So how does it help to detect the muons?
So it works because it converts when a muon passes through, it'll it'll knock a bunch of electrons loose in this, right? And when those electrons are knocked loose, when they recombine with the space where they used to be, that will release some energy. And that energy is going to look like light, will be released as light, and then we can measure that. So that's why these detectors here, it's a bit of scintillator, and then there's a very small PMT under all this black tape here. So it's
not a lot of light, which is the other thing. So it is pretty much the same as this, but the reason we don't see any muons moving through the sky is because the light that they're producing is microscopic, nanoscopic, yes, compared to the light that's just from the general room by itself.
So yeah, I guess to see these things, you have to put it inside not just one dark box, but two.
Actually, it's a beautiful thing, if I could. If we took that lump of plastic, oh, sorry, that's right, I've got to remember. If we took that lump of plastic out into the bright sun, you would see an amazing purple glow in it. And that's the actual scintillation of particles actually going through that. So we can't see that very much here. And then the black magic of what they do with the loading of these crystals is that often the glowing is not at an area that's sensitive by, say, those photomultipliers. So they put some other little dopants into there so that when the ultraviolet light is produced, it then in your level of physics, you guys, do they do fluorescence still?
Well, we did that last week.
Yeah, perfect. So, okay, yeah, okay. So perfect. So, so the charged particle that comes through will liberate electrons. Those electrons lose their energy, and it's called scintillation process. That then will often produce a color of the light that can't be seen, but then the dopant will actually absorb that light and then re-emit it fluorescently, probably towards the blue end of the spectrum, or sometimes greenish. And then the photomultiplier on the front of that phototube, that's what I was asking. I don't know what, it's not cesium, obviously, those ones. Is it?
The phototube?
Phototube, the photocathode. It's not cesium, is it? Or is it cesium?
Once again, it's a company secret. That
all right, Hamamatsu's secret. Hamamatsu bloody secret.
We also have to be careful that they're not radioactive.
Yeah,
Yes.
no, but see what will then happen, this is physics that you guys know. So now you've got a visible photon that goes through the front of that glass thing and liberates an electron from photoelectric effect. All the physics that you guys already have studied or will study at year 12. Yeah, so there's the chain of events, as Bill and Maddy described it, is the important thing. That you have some unknown particle that interacts in this crystalline structure, excites that structure, produces light. That light then travels into the photomultiplier, liberates an electron. That electron is then accelerated, and then you get a pulse from that. And all you have to do is study year 12 physics, and then you'll be ready here at first year to go and play downstairs in that lab. Yeah. They're beautiful devices. And you know, the other thing is, often in physics, you think, oh, I got invented last week. No. The sodium iodide, do you guys know when it was invented?
Well, we read a bunch of papers when we were trying to grow really pure ones that came from the 1950s and 60s.
Correct. 1956, early 1950s, late 1940s, early 1950s.
Yeah. So
this is what's going to save the world, apparently.
So the big advance we had since the 1950s, and the reason they couldn't do this, is that we have the electronics to measure it much better. So that's why I could actually show you the plot they had there. Previous experiments, they just went, oh, there's a pulse.
Something happened.
Yeah, they could maybe measure the size of the pulse if they had a really good experiment. That was about it.
That's right, 16 nanoseconds would have been unheard of.
Yes. There was another question. Yeah.
So you said dark matter didn't interact with electromagnetic force. Does it interact with the weak force?
I will again hand you back to our dark matter interaction expert.
Someone's been doing their homework. Yep, so the question for anybody playing along at home was, I said before that dark matter doesn't interact with the electromagnetic force, but does it interact with the weak force? The answer is, God, yes, I hope it does. The whole point of this experiment is there has to be some way for dark matter and regular matter to talk to each other. Because we know that it doesn't interact with the electromagnetic force, the one that we think of next is the weak. So we basically have to hope that there's some kind of particle that can talk to the weak force mediators that can then talk to dark matter and talk to the regular matter and allow them to actually have this scattering event. So the plot that I had up before of the cross section here, and remember how I said that we think we know approximately what cross sections we have. Part of the reason it's called a WIMP is because we think that it's weakly interacting, which means that it has a cross section of around 10 to the negative 40 centimeters squared. So long answer short, I hope it interacts with the weak force.
And if it doesn't, would we see it?
Not in this way. Yeah, now I'm panicking that I've banked my career on the weak force interaction.
Great.
Right.
Okay, that's really good. Maddy, I can yell, people can hear me. So Maddy and Bill, thank you for a great talk. Thank you for those of you who came tonight. I think, Cherie, you win coming the furthest from Frankston.
Yeah,
so
absolutely.
yeah, that's fantastic. Thank you for coming. And it's always good we give these lectures to enthuse people about physics because you can see the enthusiasm that our students have for it. So can we thank our two speakers once again for coming tonight? And also a very special thank you for Steve, who is just absolutely always there to set up all these amazing demos and everything else like that. So thank you, Steve, and good night, everyone.
I was also going
Oh,
to say,
yep, just you know.
just really quickly, that in 2 weeks' time, thanks. In 2 weeks' time, we've got a very special guest coming all the way from the University of Wollongong, and she is talking about how we are going to combat radiation so we can get astronauts to Mars. Okay, so she works on how we protect our astronauts and hopefully getting them to Mars. So she's making it all the way down from Wollongong. So I'd love for you to have as many people. Well, I don't think she's necessarily going to Mars, but she's just designing the suits so that we can get to Mars. So please come along, and it'd be great to have a full theatre, or, you know,
Excellent.
lots of people come along. So if you can make it, that'd be great.
And they'll be up on the website.
It is already up on the website, yes, and you can register now.
Yeah.
Cool.
Hang on. Whoa,
Whoa.
Ben James.
Ben's got a question.
Ben, a question. Thank you.
Yay.
All right. This question, without notice, goes to. Oh, Maddy's taking it already.
I guess.
Maddy, what would be some of the applications of dark matter?
Oof.
I mean, that's like asking about electricity before we even knew what an electron was. In order to properly understand how to use something, you need to know what it actually is first. I mean, there's still a bunch of people who don't even think that dark matter exists at all. So yeah, we need to work out what it is and how it can possibly interact with regular matter in order to think about how we can use it.
Would one of the, go Bill, your answer?
I just wanted to add that even before we could use dark matter, one of the things that could be really helpful is, as Maddy was talking about at the start, the standard model, the current best understanding of particle physics. We know it doesn't work. So in the same way that you couldn't make a computer without quantum mechanics, you can't make a quantum computer without the next step, quantum field theory. Who knows what we will need our next theory of the universe to be able to make. So it might be that we can never use dark matter in a useful way, but it might help us say how the universe works on an even more fundamental level, which will help us do even more things.
Well, on that note, Ben, I'd sort of say that it will make the world an even more interesting place, because on that graph that's actually up on the screen, you watch the fights about those two yellow dots. In fact, if the data actually proves to be correct, because everyone will be forced to go back to try to explain why they didn't see it and why these guys saw it. Okay, thanks everyone. Good night. See ya.
Bye.